Welcome on the day 9 of this online course, Physics with Scilab. Today we will try to obtain some important results in physics by solving first and second order differential equations in Scilab. So first we will see the growth of charge in CR circuit. So here is the CR circuit. The capacitor and resistance are connected in series. The battery of EMF E is applied across the series combination of resistance and capacitor when the position of the switch is at X. So if we apply the Kirchhoff's voltage law in this situation, then we will have this equation as I is equal to dq by dt. Then we can rewrite the equation as dq by dt is equal to minus q by cr plus e by r. So initial condition, that is when we bring the switch at position X at time t equal to 0, the charge on the capacitor Q is 0. So to solve the above equation, we have the simplest call for the ODE function. Q is equal to ODE in the argument Q0, that is initial charge, which I have taken is 0. T0 is the initial time when the charging starts. T is a time and f is a function. Now we will solve this differential equation in Scilab. So here is the code written to solve the differential equation to obtain the growth of charge in CR circuit. So CLC and CLF command. Then the function defined is dq is equal to f of tq, where dq is minus q by cr plus e by r. So this is the same equation. Then n function. Then the values of e, c, r, which are constant, are provided through the input function. Then the t I have taken from 0 to 10 with the step size of zero point 0.1. Then this is the ODE function to get the solution. So first argument, that is Q0, and it is 0. Then T0 is 0. Then T is the values of time for which I want to have the values of charge. Then the F is the above defined function. Then the command this solve, so it will display the solution on the console, and plot 2D is the command to display the plot on the graphics window. So I will save and execute. So it will first ask me to enter the value as value of voltage source. So that is, suppose I take 30. The value of capacitors, if I take 2.2 microfarad, and the value of resistance, if I take is taking 2.2, suppose mega ohm. So this is the graph which gives the growth of charge on capacitor. So using the same codes by changing some values, we can also obtain the graph for decay of charge on the capacitor. Position of the switch in the circuit will be at position Y, and therefore the E will now become 0. Therefore, while executing the program, we set the value of E to 0, and when we put the switch at position Y, the capacitor is fully charged. Suppose the charge on the capacitor when it is fully charged is 10. So I will put here 10, and now I will save and execute this program. So now the voltage is 0. I will take the capacitor, suppose 2.2, and resistance is also 2.2. So this will give me the decay of charge on the capacitor in series CR circuit. Now linear harmonic oscillator. If a particle executing harmonic motion under the action of force F is equal to minus kx, where k is a force constant and x is a instantaneous displacement from the mean position. So by Newton's law, F is equal to m into d2x by dt square. If we rearrange this equation for d2x by dt square equal to minus km into x, let the motion of the particle starts from the extreme position, that is x is equal to 1. Therefore, at t is equal to 0, x is 1. Also, at the extreme position, the velocity of the particle is 0. So, dx by dt is also 0. So, now to solve in a Scilab, we put the symbols z1 and z2 for x and dx by dt, which gives us the two first order linear differential equations, z1 prime equal to z2 and z2 prime is equal to minus km by z1. Now let's see in the Scilab. This is the code I have written for the undamped harmonic motion of a particle. So the code started with CLC and CLF command. Then the function is defined, dy is equal to f of tz, where dy1 is equal to z2 and dy2 is equal to minus k by m into z1. End function. So set the values of constant. Suppose k is equal to zero point 0.2 and m, the mass of particle, is 0.5. The initial conditions, that is t0 is equal to 0, x0 is 1, and x0 prime, that is dx by dt, is 0. Then t I have taken from 0 to 100 with the step size of 0.02. So the solution is equal to the function ODE in the first argument x0 and x0 prime, then t0, t and f. So display command will display the solution, and plot 2D function will plot the solution against time. So this argument 5 is for the color of the graph. So save and execute. So this is the solution of the undamped harmonic oscillator equation. So you can change the values. If you change the value of k, there will be change in the frequency of the sinusoidal signal. If k is increased, frequency will increase. If suppose m is increased, then the frequency will decrease. Now take a damp harmonic oscillator. Here only changes there is an additional term minus mu times dx by dt. It is a damping term. So here mu is a damping coefficient and damping is proportional to the velocity. Therefore, here is a dx by dt. So according to Newton's law, F is equal to m into d2x by dt square. And here the right hand side, if we solve for d2x by dt square, so it will be equal to minus k by m into x minus mu by m into dx by dt. So this is the initial conditions, same as in the earlier case. So if I put the symbols z1 and z2 for x and dx by dt, so I will get these two linear differential equation in first order. So now I will write the code and try to get the result. So here is the code in Scilab for damped harmonic motion. So code starts with CLC and CLF command. The function defined is dx is equal to f of dz, where dx1 is z of 2 and dx2 is equal to minus km by z of 1 minus mu by m into z of 2. End function. Then I have set the values of the constants k, m and mu. Then the initial conditions, t0 is 0, x0 is 1, x0 prime is 0. Then the time is from 0 to 100 with the step size of 0.02. Then the solution is equal to ODE function with the arguments x0 and x0 prime, t0, t and the function f. So display command will display the solution and plot do 2D command will plot the solution, that is x against t. So I will save and execute this program. So you can see the solution is damped harmonic. Similarly, if I change these values to, suppose, mu I take zero point 0.5, then save and execute. So there will be a change. If I change it to 3, so you can say it is over damped case. If I take it is equal to 1.85, so this is like critically damped. So you can change the any value from these constants and you will get the different results. Now let's see the growth of charge in series LCR circuit. It is similar example to that of the damped harmonic oscillator. So here the L, R and C are connected in series with the battery of EMF E when this switch is at position X. So according to Kirchhoff's law, the sum of the voltages across each element is equal to the total applied EMF, as I is equal to dq by dt and di by dt is d2q by dt square. This will lead to this second order differential equation, which is rearranged for d2q by dt square. So now to solve in Scilab, I have substituted the symbols z1 and z2 for q and dq by dt. So this will give me the two first order linear differential equation. Z1 prime is equal to Z2 and Z2 prime is equal to E by L minus R by L into Z2 minus 1 by Cl into Z1. So now let's try the same example in Scilab. So this is the code I have written to solve the differential equation d2q by dt square is equal to E by L minus R by L into dq by dt minus q by C into L. So it is begin with CLC and CLF command, then function dq is equal to f of tz. So t is the initial variable in the differential equation and z is the newly substituted symbol for q and dq by dt. So dq1 is equal to z2 from the first equation and dq2 is equal to minus r by l into z of 2 minus 1 by l c into z of 1 minus e by l. Then end function. The values of the constant r is 1, l is suppose 0.5, c is 0.01 and e is 10. So initial condition, when the switch is moved at position x, the charge on the capacitor was 0 and also the current through the circuit is also 0, therefore q0 prime is 0. So the time I have taken from 0 to 5 with the step size of 0.001. Then for the solution of the differential equation, the function ODE with the argument q0 prime, then t0 t and the function f. The command for displaying the solution and then the command for plotting the solution against the value of t. So now I will save and the and execute this code. So this is the oscillation created in the series LCR circuit, and you can see the amplitude is decreasing exponentially as time passes. So if I change some values over here, suppose if I take R is 10, then the solution is different. If I take it is 11, again it is different. Suppose if I take it is 15, so this is near about a critically damped case. And if I further increase this R, suppose if I set it 20, then it is over damped case. Again, suppose if I put it 25 and so on. So in this way, we can solve the many problems in physics using the Scilab and can be analyzed using the graphs. That's all for today. Tomorrow we will see the solution of Schrodinger's wave equation for some basic systems